boundary layer forming like that, right? However, what's going to happen is when you consider fluid element, this boundary layer is forming. However, previously when the buoyancy force in that direction, right, F buoyancy, now it is actually the buoyancy force is going to be in that direction. It's that component of, that's theta, it's that component of the buoyancy force that's going to scale with the gravitational acceleration, by the way. That's the gravitational acceleration over here, cosine theta. In other words, buoyancy force reduced, driving the flow. But otherwise, up to a certain extent, we are going to say that, yeah, we can actually use this as the gravitational acceleration, calculate our Grasov numbers, and we can use this g cosine theta in our formulation and stick with the remaining of the formulation as the same, meaning we can use these correlations. Let me actually talk about that. I think the mechanism of why we would have reduced convection when the plate is inclined at the bottom of the plate, can have reduced correlation is, I think, explained here. But I would like to cover more cases. So this can happen depending on the plate surface temperature versus the ambient temperature, whether we are looking at the top or the bottom of the plate, we are going to have different conditions. So we only covered one of them. Let me actually illustrate them in all together. Okay, so we can have a plate again, theta. Let's have another plate, theta. Okay, when we consider, for instance, the temperature of this plate, let's say that is Ts greater than T infinity, just like we draw. In other words, that's the hot plate. And we can also talk about, let me do some color coding. Ts is less than T infinity. That means cold plate, right? And under those cases, what we described here is going to happen. So we are going to have this boundary layer forming like that, and in the cold case, the boundary layer is going to start forming from here. But again, this argument is valid, so this is going to be happening. The velocities are in a reduced sense due to the reduced buoyancy force. Let me tell that these are cases I, case I, and that's case 2. And we are going to look at the other part now, but let me write this down. So if this angle is shallow enough that it is between 0 and 60 degrees, so it is actually either vertical or 60 degrees from the vertical, somewhere between. And we are talking about cases I and double I, 1 and 2. We can use the vertical plate correlations. There's a single L. However, if I'm using the correlations, instead of G, we are going to use G cosine theta. Anything beyond, except for the horizontal plate, is something more of an advanced topic. Things are getting more complicated. But then there is the top and bottom of the plate. For instance, when we have a hot plate, what's going to happen is there's not going to be a boundary layer particularly forming here. Instead, parcels of fluid is going to, when the boundary layer starts forming, it's going to form those plume-like structures. And they are going to, evacuate the boundary layer and go like that. And due to this fluid the hot fluid is moving up, there's going to be cold fluid coming in and filling in that space. There's going to be this enhanced effect of motion that's going to result in enhanced heat transfer. And the same thing occurs in the other cases as well. So this here, let me call this case 3. And here, the same thing happens. When the boundary layer starts forming here, there's going to be, the flow is going to start falling down. And then the relatively hot fluid is going to come and fill its place, and therefore we are going to have enhanced heat transfer. But this is really complex. It's a complex three-dimensional flow. And we are not going to be really covering it in this class for the inclined plate. Cases 3 and 4 are marked with complex three-dimensional flow. There you go. Okay, so that's going to result in enhanced heat transfer compared to the other surface of the plate. Practically speaking, you are going to need to refer to, if you're in a situation where you need to evaluate an inclined plate and you're looking at one surface of the plate where no boundary layer is forming, you need to refer to more advanced reference texts. The correlations exist, but they are beyond the scope of this class. Same goes for the conditions 1 and 2 if this angle is between 60 and 90. We don't have correlations for that. And you will need to refer to texts that are going to have these correlations in the literature. All right, after all, our class is an introductory undergraduate course. But then we have correlations for the limiting case, which is the horizontal plates. So the same phenomena occurs when we have the plates horizontally, right? So here is one plate with a higher surface temperature. Let's say there is another plate with a lower surface temperature. Imagine when we have high temperature of the surface greater than the ambient temperature. You need to reason this, right? So the flow is going to come up, but then it's going to impinge on the surface and form a boundary layer here. But here it is free to go up. Likewise, when you consider a cold plate, now you are going to have flow coming in and impinging on the surface, and it needs to travel around the plate to actually go down. It can freely move on this surface. So depending on whether we are looking at a hot plate or cold plate, this corresponds to what we called case I in the previously. This corresponds to what we called case 2, case 3, and case 4, right? So these are what we are talking about. So whether we are looking at a hot plate and which surface of that plate versus cold plate, which surface of the cold plate, we have different situations. And we have correlations for those. By the way, I think I didn't do that. I will decrease the size of this. It is too big, the color markers. Okay, so let me bring in the correlations, if I can. Okay. So for the upper surface of the hot plate and lower surface of the cold plate, these are where we are going to have enhanced heat transfer. We are going to have these correlations. All of them are in the form of what we described earlier as C Rayleigh number raised to the power some exponent, as you have seen. And these are corresponding to particularly those enhanced heat transfer conditions. When we don't have correlations for inclined plates with a certain angle, we have correlations for horizontal plate for those enhanced conditions. And for the lower surface of the hot plate and upper surface of the cold plate, remember that this approximation is not valid for angles larger than 60, and 90 is definitely larger than 60. For horizontal plate, you have another correlation. You can use this correlation. The problem is symmetric, again, just like the vertical plate for hot and cold plate here. And therefore, you can use the same correlation for both cases. So this is corresponding to cases 1 and 2. Now, one question over here is which length scale you are going to be using here. We have an expanded definition of length here. When we had an vertical plate, the length was clearly defined. That was a direction in which the boundary layer would develop. However, this time we are going to actually need to consider the characteristic length. You can have a plate size, like you can have an arbitrary shaped plate, by the way. It can have a certain surface area and a perimeter. Under those cases, you would define the characteristic length as the surface area divided by the perimeter, and you are going to base your Rayleigh number calculations based on this characteristic length. Okay, there you go. Any questions? So if no questions, I have a question for you. Here's a question. Please answer as A, B, or C. So which condition is likely to produce the greatest rate of heat transfer? I'm going to go ahead and label those as you're going to have 3 correlations. And overall, thinking about what conditions those correlations are valid, what happens under those cases, why don't you go ahead and say that I'm going to obtain the greatest heat transfer when using that correlation, A, B, or C. Let me start a poll. Again, these conditions doesn't have to be the same. They are different, right? So for instance, for C, we are looking at the lower surface of a hot plate. A and B, we are looking at the upper surface of the hot plate. But then A and B are, there are 2 correlations for different Rayleigh number regimes. So that's what I'm actually looking for. Consider which one of those correlations, when used, is going to result in highest Nusselt numbers or highest heat transfer, rate of heat transfer. That's the question. Okay, half of the class have answered. How about the other half? Are they still thinking, or? Let's wait for a minute more. 15 people have responded out of 30. That's too low for class participation. Take your best guess. There is no, you don't lose anything by answering. So take your best guess. Let's hear from you guys. You don't need to draw, plot anything. You can infer the result by inspection. Okay, I'm only concluding that the remaining people are not here. Like 12 people out of 30 are simply here by electronically, but physically, and they're not here. And just don't come to the class. You don't have to. You're not taking attendance. Okay, so 18 people have responded. And the results are like, it is posted in the chat window. And I'm happy to see that people on majority actually answered part B. And that's the correct answer. And first of all, let's distinguish between AB and C. Lower surface of a hot plate. When you look at the correlation ranges, imagine that we are considering a Rayleigh number of 10 to the power 8, okay? Comparing those two correlations, you are going to see that this correlation is going to result at higher heat transfer than this correlation. The distinction is that notice that lower surface of the hot plate is where we have this boundary layer forming. So we said that that's heat transfer, but this top surface has enhanced heat transfer because of these jets or plumes or parcels of fluid that is moving up freely without forming a boundary layer, and they are being refreshed by the fresh medium, fluid coming from the quiescent region. Therefore, there's enhanced heat transfer for A and B. And when you compare A and B, you are going to see that as we increase the Rayleigh numbers, we are going to end up with higher values simply because when we increase the Rayleigh number, first of all, we are going to transition to turbulence. And that's going to result in higher numbers. And numerically comparing, notice that this exponent is when you increase Rayleigh number, this exponent being larger than the other two exponents dominates, and it is actually this Nusselt number is increasing faster than the Rayleigh number compared to the others. So there are several reasons why you can say B. But some people said C, so they are, I think, understand why they are wrong. And comparison of A and B is simply because this is going to return lower results for most of the Rayleigh numbers that we can consider within those ranges appropriate for each correlation. Anyway, okay, so let's go back to our discussion. I'm going to solve an example problem. That's problem 935. Let's start a new slide here and paste it in between. Okay, so airflow through a long 0.2 meters square air conditioning duct maintains the outer duct surface temperature at 10 degrees Celsius. If the horizontal duct is uninsulated and exposed to air at 35 degrees Celsius in the crawl space beneath a home, what is the heat gain per unit length of the duct? So what's happening is that we have an air conditioning duct. Let me bring an inset of the problem. It's a square cross section. Also bring a square cross section. There you go. Here is my duct. And what we are having is that it has an edge. It's a long duct. And it has an edge of L is equal to 0.2 meters. And since it's square, this is also L. I like this example problem a lot because you got a chance to observe all of the discussion that we made here. So the surface temperature of the duct, this air conditioning duct, there's cold air flowing inside. You're not considering that. That's less than T infinity. What is T infinity? it's 35 degrees Celsius, and it's air that's outside. So this example is really nice because we have 4 surfaces, and each one of those 4 surfaces actually are associated with a certain condition that we have covered in this class. So if we were to label those individual surfaces starting from this and going clockwise, so Ts is less than T infinity, meaning we have cold surfaces everywhere. And when you look at 1 and 3, we are going to end up with these are vertical plate. However, since it's a cold surface, the boundary layer is going to form like that, right? And how about 2? In 2, we are going to have top surface of a cold plate. It's horizontal. Cold plate, top surface. Okay, maybe a comma is unnecessary here. Horizontal cold plate. And 4 is, again, horizontal cold plate, bottom surface. Great, so remember the flow characteristics happening. So boundary layer is going to form like that, but here it's free to, cold air is free to fall down and get refreshed by relatively warmer air from the surroundings. Okay, let's evaluate the fluid properties and evaluate what we need to do. Let's start with the vertical plate. Fluid properties. I'm rushing ahead of myself. Fluid properties. Film temperature, that's 295 Kelvin. And the properties for air at that temperature is going to be density equal to 1.1847 kilogram per cubic meter. Kinematic viscosity is 15.45 times 10 to the power 6 meters square per second. Thermal conductivity is 25.9 times 10 to the power minus 3 watt per meter Kelvin. And the Prandtl number is 0.708. We have one more property. Remember, thermal expansion coefficient 1 over T infinity. That's going to give us 1 over 295 Kelvin. And we can write it like that in our formulations. We don't need to write it in decimal notation. So let's take a look at the cases 1 and 3. As we said previously, 2 things. First of all, whether it is on the either side of the surface doesn't matter. They are essentially the same problem, right? 1 and 3 are the same problem. They are the problem of a vertical cold plate. When it is cold and also the surface temperature is constant, we are going to calculate Grashof number as G beta T infinity minus Ts to make it positive, right? We are taking the absolute value of the temperature difference. And that's going to give us 9.81 times 1 over 295 times 35 minus 10, and the length is 0.2 raised to the power 3 divided by 15.45 times 10 to the power 6 squared. And we are ending up with the Grashof number for that surface as 2.786 times 10 to the power 7. Okay. So then we can calculate Rayleigh number as the Grashof number multiplied by Prandtl number. That's going to be 1.973 times 10 to the power 7. We can immediately see that that's less than 10 to the power 9, and therefore we are talking about laminar flow again throughout the plate. Okay. So which correlation should we use? In the previous example, we used the similarity solution because we didn't know any better. How about using equation 9.27 now? Because that was particularly correlated based on experiments using, let me move this a little bit up, using, experiments. So it was for laminar flow. So it is more accurate than we could use for the similarity solution. And it's also giving us the average Nusselt number. Maybe I forgot to mention that you probably have noticed in the correlations, these are average Nusselt numbers across the plate. So they are saving us the trouble of somehow converting the local Nusselt number, integrating it over the surface, right? So you don't need to do that. This is the average Nusselt number plus 0.67 times 1.973 times 10 to the power 7 raised to the power 1/4 divided by 1 plus 0.492 divided by 0.708 raised to the power 9/16, and that's raised to the power 4/9. Quite a complicated expression, so you may want to calculate this part by part. And to do that, you are going to obtain 3494. And from here, h is equal to 3494 times 25.9 times 10 to the power minus 3 divided by the length, that's 0.2. And here, that let's call this h1 is equal to, that's h1, is equal to h3 associated with those surfaces. That's going to be 4.52 watt per meter square Kelvin. Okay. So how about the second surface? The second surface is horizontal cold plate, and it's top surface. When you look at the equations over here, it's equation 9.32 is the one that is saying us the top surface or upper surface of the cold plate. So that's going to be equation 9.32. How about the other one, horizontal? Well, I think that's not 3, that's 4. The surface 4 is horizontal cold plate, bottom surface. Which equation we are going to use? 9.30 or 9.31? So that's the question. Is it clear? Okay, so here we have two equations. They are for different Rayleigh number ranges. Which one we are going to pick? Based on our Rayleigh number knowledge, we can pick, but that wouldn't be accurate, right? Because we need to calculate the Rayleigh number again, because for those correlations, the definition of Rayleigh number is different. Okay. Maybe we are going to end up with the same result, by the way, as a heads up, but we need to calculate it. So in order to do that, we need to understand how we should calculate the Rayleigh number. That's a long duct. And we need to have, that's actually the cross section, L. And let's assume for the time being, we have a certain very long distance LP, right? So the characteristic length is equal to the surface area divided by P. And that's going to be equal to L multiplied by LP divided by the surface area 2 times L plus LP. And however, this LP is much larger than L. That's because it's a long duct. So under those cases, the characteristic length is going to boil down when you do the scaling analysis. This L is going to disappear from here. So we are going to have L multiplied by LP divided by 2LP. And that's going to be L over 2. That's going to be 0.10. So it turns out that we need to base our Rayleigh number on over the half the distance. That actually makes sense, particularly if you're talking about, let's say, this configuration, right? So when we say we are talking about actually this configuration, let me check. Well, we are talking about this configuration for surface 2. Let's discuss that. So when we are using one of those correlations like 9.32, we are going to be using the Rayleigh number based on half the length of this plate. So it makes sense because as you see, when the flow structure forms, it is forming a boundary layer across half of the plate. So that's kind of the approximate understanding. Maybe you may want to remember that. That's not always true, but that's true for a long duct. If you have an arbitrary shape, you need to calculate it using this. Maybe you can have a disk, and that disk is going to have a different characteristic length compared to this one. Okay, anyway, so let's continue. Under those cases, we are going to calculate the Rayleigh number again. That's 9.81 times 1 over 295 times 35 minus 10 times 0.10 raised to the power 3 divided by 15.45 times 10 to the power minus 6 square, 0.718. And the Rayleigh number is going to be 247 times 10 to the power 6. That's within the range of 10 to the power 4, 10 to the power 7. So we are going to be using equation 9.32 for 2, because that's the only choice we have. Now let's check the range still. So it is between 10 to the power 4 and 10 to the power 9. So we are within the range with 10 to the power 7. Equation 9.32. The Nusselt number is going to be equal to 0.52. Rayleigh number raised to the power 1/5. And that's going to be 0.52 times 2.47 times 10 to the power 6 raised to the power 1/5. And that's going to be 9.88. And from here, H2 is equal to 9.88 times 25.9 times 10 to the power minus 3 divided by 0.10 again. Remember that we are not using L, we are using characteristic length. The Nusselt number is also based on the characteristic length. And H2 is going to be equal to 2.55 watt per meter square Kelvin. Okay. How about the last one? We are going to pick, because Reynolds number is less than 10 to the power 7, we are going to pick the first equation in the set of equations. We have equation 9.30, and that means Nusselt number is equal to 0.54 Rayleigh number raised to the power 1/4. And that's going to be 247 times 10 to the power 6 raised to the power 1/4. That's going to be 21.41. And from here, you can calculate the H4 as 5.55. You can connect Nusselt number to that watt per meter Kelvin. All right. So at the end, we are going to end up with what was being asked. I forgot. What is the heat gain per unit length of the duct? So we are considering the heat gain all over the surface. So, and that's per unit length. We can calculate this as the total heat transfer rate divided by this, what did I call that? LP, LD? For some reason I called it LP. Let's continue with that, LP. And that's going to be equal to summation on all surfaces, or let me put it this way, simply, heat transfer per unit length. And that's going to be summation over HI multiplied by L multiplied by T infinity minus Ts. That's going to give us 4.52 from the first surface plus 2.55 from the other surface. 4.52 again from the third surface. This is the same but just symmetric. And then the bottom surface is enhanced heat transfer with N 5.55. Particularly compare those two values for the top and bottom surfaces, and you can see the marked change of convection heat transfer coefficient. And at the end, we are going to obtain prime is equal to 85.7 watt per meter. That's our conclusion or answer for the problem. Do you have any questions? Why didn't we use equation 9.30? Oh, okay, so we were actually dealing with the second top surface of the cold plate. So that was the second case right over here. Therefore, we are using equation 930 for that. Okay, I see. So you are also have seen why this will be the case. Okay, any other questions? Okay, so for maybe last 5 minutes, I'm going to discuss about another geometry. So we covered vertical plate. We covered different angles at which we can keep that plate with inclined or horizontal. We talked about vertical cylinder, but we simply said that for a very large diameter compared to some criteria, we can actually treat this as a vertical plate. We can unroll it and do our calculations like that we can imagine it unrolled and do the calculations that way. But then we can have horizontal cylinder in the flow. All right. So what's going to happen is that's essentially what we discussed in the beginning of the class. You can have a wire with a diameter d, and it can be like this into the depth, right? And it can have a certain length, with length much greater than the diameter. Under those cases, imagine that's a hot wire, so that the surface temperature is greater than the ambient temperature. Then we are going to have this plume forming upward. And we have seen examples of that. We even saw some videos of plumes forming like that. So there's clearly going to be convection heat transfer that is depending on formation of this boundary layer and then detachment of the boundary layer. The situation is kind of similar to what we have considered in cylinder and cross flow. Remember the variation of Nusselt number across the surface, starting from the forward stagnation point. We would have this Nusselt number depending on the angle, but it would also depend on laminar or turbulent conditions, whether where would the flow detachment would occur over the surface and so on. It's complicated. However, the heat transfer correlations correlating that are not that complicated. So let me show you one. When you consider it in an average sense, average Nusselt number can be again correlated with an expression. See, Rayleigh number, this is based on diameter now. Both Nusselt number and Rayleigh number are based on diameters. And these coefficients CNN now are depending on the Rayleigh number range. So here is a table 9.1 that we can use to determine those coefficients for a horizontal circular cylinder. Hassan, I'm going to talk about this after finishing this. I think we are going to have time to address your question at the end of the class. Okay, so, but then Churchill and Chu wouldn't be find this sufficient. They actually said that, how about correlating, coming up with a single correlation for the whole range? And this is for all the range until Rayleigh number 10 to the power, less than 10 to the power 12. And you can use that correlation. That's it. That's for the horizontal cylinder. You have two options. I didn't go into trouble of comparing them, plotting them individually, and looking at how similar or different they are. You can do it to see. You have two options in essence. I mean, we are not suggesting any one of them over the other here. But if you like to be on the safe side without checking the range, you can actually use this correlation and be sure that it is applicable for whatever Rayleigh number range you have, unless you have very high flow rates or very high Rayleigh numbers. Okay, so this is for cylinders. Let's talk about sphere as well, get this out of the way. And here is the sphere case. And this correlation is valid for Prandtl numbers greater than 0.7 and Rayleigh numbers less than 10 to the power 11. Notice this two factor over here. This two factor came up previously as well when we were discussing sphere in cross flow. And this two factor, if you actually did the math, that would correspond to heat transfer from a sphere that is embedded in an infinite medium. Remember 2D conduction chapter 4, the shape factors. You can go to the table and find out this associated shape factor, and that's essentially what if the condition when the fluid is stagnant, right? So that's the baseline where we are going to have heat transfer by conduction only, and that sphere in a stagnant infinite medium. That will give us Nusselt number is equal to 2. You can go back and trace that. And finally, I would like to recommend checking out tables 9.2 and I think 9.3 as well for a summary of convection correlations for immersed geometries. This is a great summary of what we have discussed. Table 9.2, but I believe table 9.3 also includes the correlations for cylinder and sphere. I didn't check. But you can look at your textbook. A summary of free-convection correlations for immersed geometries. Okay. Any questions other than Hassan's question? You can write in the chat window. Now, Hassan is asking about what we did in distinguishing the bottom and top surface differ from each other. So I think he's referring to here. This is the top surface convection coefficient. That's the bottom surface convection coefficient because of the flow structures. Remember that when we discussed horizontal plates, we said that when the top surface of a cold horizontal plate is going to have some impinging jet, but it's like a boundary layer forming across each half of the surface, and then it's going to fall down from the sides. And that's okay. So there is going to be a certain amount of heat transfer here. Here, the boundary layer is going to be continuously interrupted at the bottom surface of the same plate, let's say. The boundary layer is going to be continuously interrupted and get refreshed by a warmer fluid from the surroundings. So we are going to have enhanced flow and some fresh fluid coming in that's going to cause a complex 3D flow with enhanced heat transfer. And as a result, we have different correlations for them. As you can see over here, that was part of our discussion of which correlation would give you the largest convection heat transfer coefficient, for instance. And it turns out when we use this correlation and this correlation, A and C, right, in our example problem with the same Rayleigh number, we ended up with a twofold difference. Correlation A resulting in a larger result than correlation C. Is that clear? Okay, all right, Hassan. Burhan is asking a question. Let me. Okay, so do we have the slides? I think we do. Burhan is asking about what's happening to the pressure variation within the boundary layer across y direction. As far as I can understand, that's the question. And in order to answer that question, I would recommend going back to chapter 6 for once, looking at the similarity, let's say looking at the non-dimensional form of boundary layer equations. And this is the x momentum equation in this direction. We also have a y momentum equation we are not even writing down. But when we covered chapter 6, I briefly went over the y momentum equation and showed that the only term that is remaining in the y momentum equation is the pressure term. dP by dy is equal to 0. Meaning that it turns out within the boundary layer, the pressure variation with respect to y direction is 0. Therefore, pressure is not a function of y. And therefore, whatever the pressure at the edge of the boundary layer, which is corresponding to the free stream, that's forced convection, right? And it's going to be same as the pressure at the same x coordinate, but at the surface of the plate. So there is no pressure variation in y direction. The similar situation happens here when we are developing the boundary layer over a vertical plane. Does this make sense? And that's how we can actually write this term. dP by dx within the boundary layer is equal to same as the dP by dx within the quiescent region, because dP by dy is 0 coming from y momentum. All right. Okay, great. That's it then for today. And next week we are going to continue covering convection, and hopefully we'll be finishing the convection, free convection chapter. I will see you next week on Tuesday.